Okay, this third version of the program is going to implement the full algorithm that you can see here in the instruction for this exercise. We are going to add two extra semaphores, empty and full. The general problem for the producer-consumer, which is also referred to sometimes as the bounded buffer problem, is that between the producer process and the consumer process, you are going to have more than one data slot available. Our simplified version here has only one int that can be transferred at a given time, between the producer and the consumer, but the general problem has a fixed number of such slots. Well, for that reason, the empty and full semaphore are used as counting semaphores. The empty semaphores represent the number of slots which are empty at any time available, and the full semaphore the number of slots that are full. So in our case, since we have only one slot, these are going to be degenerated down to binary semaphores, okay? When we start, empty needs to be initialized to 1. There is one data slot in the shared memory that is available. Full needs to be initialized to 0. 0 of those one data slots are being used right now by the producer. So every time the producer wants to produce something in the shared memory, it needs first to ensure that there is at least one empty data slot. This is done by doing a down operation on the empty semaphore. Remember, initially the empty semaphore will be 1, so the down operation will succeed. Then you still do everything you did here for granting mutual exclusive access to the shared memory, but when you are done filling up one of the data slots of the shared memory, you call up on the full semaphore, meaning, hey, there is one slot now that is filled with data. The consumer will use the same logic but completely reverted. The weight is based on the full semaphore. I need to have at least one data slot full to be able to consume any data. And once I'm done consuming a data, I release one more count of empty data slot by doing an up operation on the empty semaphore. So let's have a look at how it looks in the code. I did a simple copy of version 2 files into version 3. So hold on a second, let me remove this window out of the way. There we go, we have our producer and consumer here. Let's start with the producer. We need to add a couple more semaphores, so let's get started with that. We have here semKey mutex, semID mutex. Well, I need a semKey full. Oops. I need also a semKey empty. Same thing here, I need a semID full, I need a semID empty. And I'm going to have some boilerplate code here to just get those key values from the user. So instead of semKey mutex, semKey empty. And there we go, change the name of the variable as well, of course. And instead of semKey empty, the third one will be semKey full. So I have 3 variables this time to hold my keys for my 3 semaphores, and I read them all from the user. Once I'm done with this part, I'm going to move to creating the semaphores. So once again, that's going to be mostly cut and paste here. The same way I created mutex, I'm going to create empty. So I get my semID from the key. And the same way I create empty, I'm going to create full. There we go. Let's align this nicely. So that takes care of the creation of all of my semaphore, create from scratch. What about initialization? Well, let's see. Mutex need to be initialized to 1, that's still true. What else? Empty need to be initialized to 1 because originally my shared memory segment is empty, so the one data slot there is available. And full doesn't need to be actually initialized. Let's scroll down. What do I have left to do here? Well, everything that concerns the shared memory is going to be pretty much the same. And then here, I'm going to follow my algorithm as specified in the instruction for this exercise. Before to be able to produce, I need to do a semdown on semID empty. Once I'm done producing, I do a sem up on sem ID full. There's one more slot that is full. And that's the core logic, okay? Detaching the shared memory is always a good idea. Destroying here, let me see. I was going a little too fast here. Detaching the shared memory, okay, done. Destroying the semaphore that I used. I'm going to do it at the same spot I was destroying semID mutex. So now I destroy also semID empty. And I destroy semID full. And that should be it for the producer. So let me save. Let's check if there are typos, things missing, things of that sort. I'm going to do, should have it somewhere here. These are the CP I used, GCC, Roshkind, producer v3. Okay, sounds good for now. So I'm going to move to the consumer and then we're going to start testing. So for the consumer, I'm going to reuse some of the code I used already in the producer, okay, because some things are going to be totally identical. So for instance, well, here I need extra variable, right? I'm going to name them the same way. Same key empty, same key full, and same ID empty, same ID full. I'm going to reuse exactly the same code here than the producer to read values from the user. There we go. That should work just fine. And later on, I'm going to open my semaphore instead of creating them from scratch. So that's going to be a semID empty equals sem open, this time sem key empty, and semID full equals sem open, not creation from scratch, sem key full. Setting the size, I don't have anything to do. Initializing the semaphore, I don't have anything to do. But when I come here and I'm ready to play with the semaphore, I'm going to have to implement the logic described in the algorithm, in the instruction for this exercise. That is sem down, semID. The first one will be, I am the consumer, so full. And the second will be sem up, semID underscore empty. And the logic once again is, the logic is once again, when I am done consuming, sem up is freeing a new empty slot. When I am about to consume, I need to make sure I have at least one full slot available. Okay. R&D, etc., all of this, waiting for an arbitrary number, a random number of seconds is going to be the same. And I'm pretty much done with the consumer. Let's take a look at how this compiles, and then we're going to test it. So I'm going back to Conqueror. That's the producer I just compiled. Let me compile the consumer. Looks good. And now let us test them. Prod v3. SHM key is going to be 123, mutex 111, 222, 333, and I'm not going to press enter just about now. I'm going to start the other one. Cons v3, 123 for shared memory, 111, 222, 333. I'm not pressing enter. Okay, let's start the consumer. Give it a head start. Let's start the producer, sorry. Now let's start the consumer. You can observe that things are going a lot slower. Why? Well, if the producer sleeps 5 seconds here for the first data release, the consumer sleeps 3 seconds only, the consumer will still have to wait for the producer to be done before to read 0, the first data being exchanged. But you can see that the benefit of that is that we have here 0, 1, 2, 3, 4, 5, 6, etc. 0, 1, 2, 3, 4, 5, 6 read. So we don't lose anymore any data. So we do have synchronization between the producer and the consumer. And then I press enter, and everything is destroyed, deallocated, etc.